Hi, I'm Kordian Gontarska, a research associate at the Hasso-Plattner Institute, Potsdam, Germany. Welcome to my talk about the evaluation of load prediction techniques for distributed stream processing, which I worked on together with Geldenhuys, Dominik Scheinert, Philipp, Wiesner, Andreas, Polze, and Lauritz Thamsen from the Technische Universität Berlin. I'll first give an introduction, then I will analyze the problem at hand and present our methodology to approach the problem. This is then followed by the experimental results and ends in a conclusion. Distributed stream processing systems, in short DSP, are responsible for extracting valuable insights from large streams of real-time data. Some might know technologies like Flink, Storm, Heron, or Spark. Application areas include IoT data processing, clickstream analysis, network monitoring, fraud detection, spam filtering, and news processing. These jobs require high throughput rates and low end-to-end processing latencies to support time-sensitive decisions. Input streams, however, are dynamic in nature, and processing loads therefore have the potential to change significantly over time. Consequently, DSP systems are able to scale horizontally across a cluster of commodity nodes in order to accommodate different processing loads. With this potential for workloads to fluctuate over time and the ability of systems to dynamically adjust configurations at runtime, research into approaches for the adaptive management of resources has grown in popularity in recent times. Interestingly, an increasing number of approaches use time series forecasting, a more generalizable and proactive basis for making good decisions. Through forecasting what is to come, we are better able to anticipate and plan for the future, adjusting configurations before it is too late. The use of time series forecasting is not new in the context of DSP systems, but in most cases it requires experts to pick the appropriate method and configure it to the situation at hand. Moreover, to the best of our knowledge, no comprehensive comparison has been conducted thus far. Previous attempts at comparing these methods were inconclusive and present results obtained from a small number of datasets. Let's look into the problem analysis. We identified 3 use cases where accurate load prediction would be beneficial for efficiently running DSP jobs despite varying input rates. First one is dynamic scaling. The scalability of DSP systems is achieved by partitioning the entire data streams among the data parallel task instances that are deployed across clusters of computers. Many DSP systems have the ability to scale dynamically, yet the difficult task of deciding by how much and when is typically still left up to the user. Furthermore, the current research on this problem relies on coarse-grained metrics such as CPU utilization, throughput, and back pressure, which tend to show incorrect provisioning, oscillations, and long convergence times. For this use case, a shorter prediction time horizon is important, for example 5 minutes. Next is the timing of live migrations. As DSP systems approach even greater scales, the number of things that can go wrong increase as well. Live migrations allow administrators to transparently tune the performance of computing infrastructures when performance degradations in cluster nodes are detected, migrating system functionality and state over the network. Much of the research in this area is focused on the methods for detecting these anomalies. However, the question of when these preemptive actions should take place is likewise an important question to answer. Here, time series forecasting can provide a way to automate this process by predicting periods of low utilization where changes to the cluster will have a less impact on the performance. For this use case, a mid-range prediction time horizon, like for example 15 minutes, is important. And the last one is the automatic system tuning. Self-tuning systems are those which are capable of optimizing their own internal configuration parameters in order to maximize or minimize the fulfillment of one or even more objectives. If done correctly, this can yield systems which are more performant, cost-effective, reliable, and power efficient. In order to achieve this, approaches within this domain commonly conduct profiling runs and/or use historical data in order to model performance behaviors. Time series forecasting allows to determine the proper timings of these updates. For this use case, longer-term forecasts with hourly time horizons are most useful. DSP systems come with their own specific requirements, which need to be taken into consideration while designing approaches to load prediction. We identified and defined the following requirements. First, minimal configuration. Solutions should follow a plug-and-play approach. User configuration requirements for tuning model hyperparameters should be kept to an absolute minimum. Then we have limited model inputs. Concerning the amount of data that is used for initial training, this depends on how long the DSP job has been running and the availability of metrics data. The default retention periods of time series databases such as InfluxDB and Prometheus commonly used for storing such data is 7 and 15 days respectively. Thus, a limited amount of training data should be expected. Then we have the frequent model updates. As new observations are continually being produced, models should consider these for their forecasts such that the quality of the predictions does not degrade over time. This can be achieved by periodically retraining the models or updating them before each new prediction with the latest observations. Then we have the variable forecasting length. Models which support multi-step time series forecasting are required. Understanding how expected workloads change over time is an important aspect to consider when designing strategies for the aforementioned use cases. Solutions should have the ability to incorporate various sample rates to match desired time horizons. And I will now talk about our approach and how we set up our experiment. We have considered the following commonly used time series forecasting methods. First, we took baselines, last observation and last day observation. The two performance baseline models are established by taking either the last observation and projecting it forward for the length of the forecast, or by taking the observation from before 24 hours. Then we have our classical methods, where we begin with SES and TES. Single exponential smoothing, SES, introduces exponentially decreasing weights, allowing to prioritize more recent observations and thus capture latest trends. We performed a grid search to find the optimal configuration. Holt and Winters extended SES and developed triple exponential smoothing, TES, which allows incorporating trend and seasonality. Then we have ARIMA and SARIMA. Autoregressive integrated moving average, or in short ARIMA, is a widely used approach for time series forecasting. And due to the seasonal nature of the datasets, we included seasonal autoregressive integrated moving average, or short SARIMA models, which add seasonality to ARIMA models. Then we used Prophet. Prophet is a popular open source time series forecasting library developed by Facebook. It aims at making time series data analysis available to non-expert users. We included deep learning methods, two, which of the first one is CNNs. Convolutional neural networks, network architectures have been used successfully for time series prediction on multiple occasions, as they allow for increased training speed and deep architectures due to shared filters. We also used GRUs. Recurrent neural networks, in short RNNs, allow for the memorization of past observations, which makes them suitable for applications on time series. We chose gated recurrent units, GRUs, which are a special form of RNN cells. Our main objective is the symmetric mean absolute percentage error, or in short SMAPE, SMAPE, which is commonly used for forecasting problems when dealing with data sources of varying value scales. SMAPE is defined as follows and delivers an error value between 0% and 100%. It is furthermore utilized as the loss function for our deep learning methods, as it is invariant to absolute errors. We selected 9 heterogeneous and univariate datasets to investigate the applicability of our chosen methods on varying data. These datasets represent the expected load in a DSP system. The time series describe the sum of the events entering the source operators of a DSP job per second. We first have IoT datasets, where we have an IoT traffic dataset. It's a synthetic dataset created using the Sumo traffic simulator and the Tapas Cologne simulation scenario. The data represents the number of vehicles on the streets per second over time. Then we have the NYC taxi dataset. It's a dataset from the NYC Taxi and Limousine Commission on taxi rides in New York City. We aggregated the number of taxi rides of all providers during every 5 minutes over a 3-week period in January 2020. Then we have the cluster trace datasets, beginning with Alibaba. This is production data originating from an Alibaba cluster in 2018. We extract the start time of batch tasks over a 7-day period and aggregate them. Then we have the Google cluster traces. Those are workload traces recorded from 8 different Google Borg cells during the month of May 2019. From this trace, we extracted information about instance events over a randomly selected period of 21 days. And the last group are clickstream datasets, where we begin with Wikipedia page views. We used the Wikipedia API to extract the number of page views per hour for a period of 3 weeks in July 2019. The procedure is conducted both for the German and English Wikipedia and thus results in 2 different datasets. Then we have data from Awazu. This dataset is created by using a click-through rate prediction dataset from Kaggle, aggregating the clicks per hour over time. Then we have the Hortonworks dataset, clickstream events taken from a tutorial on visualizing clickstream data provided by Hortonworks. We extracted the event timestamps on a per second granularity and aggregated them to the respective granularities. Then we have Retail Rocket, an e-commerce data containing events of the Retail Rocket recommender system. We construct our dataset by aggregating behavior data such as click events over a 3-week period. Here we can see a 2-day snippet from a clickstream dataset at a 1 hour, 15 minutes and 5 minutes sampling rate. However, some datasets originally only come with a sampling rate of 1 hour. We changed that by estimating the expected relative error from the remaining datasets when interpolating them to a 5-minute sampling rate. We then added normally distributed noise to the new interpolated datasets using the expected relative error. Finally, we resampled these new datasets also to a sampling rate of 15 minutes. We adjusted all datasets by scaling and shifting them to have the same mean message per second rate and the same standard deviation. This was mainly done to make them realistic event rates in DSP jobs. These adjustments result in the final datasets at 3 different sampling rates. The training of the models as well as inference was conducted on a dedicated machine equipped with a GPU. The details can be found in our paper and in our GitHub repository. Each of our experiments examines the forecasting capabilities of a certain method on a specific dataset. For each sampling rate, we define a different forecast horizon. For the 5-minute interval, we aim at predicting only the next value, so in 5 minutes. The 15-minute interval comes with a horizon of 4 values, so the next hour, and the 1-hour interval is associated with a prediction horizon of 12 values, or 12 hours. This reflects our different use cases. Here we can see all the datasets we used at a 1-hour sampling rate with dataset splits being highlighted. For the deep learning methods, we split each dataset along the time domain into training, highlighted in white, tune, highlighted in gray, and test, highlighted in pink, subsets with a ratio of 3 to 1 to 1. The tune subset is used during hyperparameter optimization to abort unpromising trials and to determine the best trial. All other methods, or the classical, conduct a split into training, white and gray, and test, pink, subsets with a 4 to 1 ratio and thus effectively train on more data. A short remark about the model training and configuration. For all classical methods, the AIC estimator is used to determine the best hyperparameters. We fit the level smoothing factor alpha of SES models. For TES models, we additionally fit beta and gamma, the smoothing factors for trend and seasonality. For training ARIMA and SARIMA models, we perform a hyperparameter search on all parameters, and in the process, we assume a seasonal period of 24 hours. For the deep learning models, we search for optimal configurations over a variety of different hyperparameters, such as number of layers, number of neurons, learning rate, and dropout rate. For both CNN and GRU, we are moreover especially interested in the optimal length of input sequences extracted from the training data. Further details can be found in our repository. For profit, the hyperparameter optimization and fitting is handled entirely by the library. The experimental results. Here we can see predictions from all methods on a 1-hour sampling rate clickstream test set, together with the original data in black. The deep learning models, as well as profit, fit the seasonal pattern well, while the remaining classical models are more responsive to noise. Methods which do not capture seasonality in their models perform poorly on the task to forecast the approaching 12 hours. I will shortly mention some limitations we encountered in the experiments. Since Prophet is primarily designed to detect long-term seasonality, it appears to struggle with short sampling rates. When fitting it to data with a 5-minute or 15-minute sampling rate, the library only predicts hourly data and interpolates between these data points during prediction. We therefore decided to only include the hourly sampling rate model into our evaluation. Another problem is that the coefficients for the SARIMA models are being computed analytically. At a sampling rate of 5 minutes and a daily seasonality, one seasonal period consists of 288 observations, which renders the computation infeasible in our scenario. Here we can see the SMAPE scores. The methods are on the x-axis. Each sampling rate has its own diagram with the 1-hour sampling rate at the top. The resulting SMAPE is averaged over all datasets. We can see that across all datasets and sampling rates, the deep learning methods are the best or among the best performing methods with a stable prediction performance. The stability aspect also holds true for TES, whereas all other classical methods are either experiencing difficulties for certain sampling rates or are even not applicable to them due to their technical limitations. We identified that the deep learning methods performed best across all use cases, with no universal alternative from the classical methods. TES outperforms our baselines across all sampling rates. Meanwhile, ARIMA shows good prediction capabilities on the 5-minute and 15-minute sampling rates datasets, yet fails to capture seasonal patterns present in datasets with an hourly sampling rate. SARIMA works well on hourly data as it has short seasonal patterns and thus states a good alternative from the classical methods, but it struggles with long-term seasonality as present in the data sampled at 15 minutes. GRU are the best performing models for the use case of 15-minute sampling and a forecast horizon of 4 samples, and are closely followed by the CNNs. ARIMA and TES perform reasonably similar and make for good alternatives from the classical methods. While the GRU models perform best on predicting observations with a sampling rate of 5 minutes, ARIMA performs almost as well. In conclusion, we find the DL methods, or the deep learning methods, as well as the TES to be the most universal predictors. We also measured the time needed to find optimal hyperparameters and fit the respective models, as well as the average time it takes a model to predict the next observations and possibly fine-tune it to the most recent observation. The results for the training time can be seen here. As expected, the required time for training and fine-tuning depends on the amount of available training data, which is shown by the difference between the various sampling rates. The higher the sampling rate, the more data there is. The methods based on exponential smoothing are quicker than the ARIMA variants. It can also be seen that the more complex variants of the respective methods, here the TES and SARIMA, require more time due to the extended hyperparameter search space. In comparison, Prophet is slightly more time demanding than exponential smoothing, yet notably faster than the ARIMA methods. Although the deep learning methods are not directly comparable due to the utilization of different hardware, we use GPUs, it is worth mentioning that the training in general takes relatively long. In this figure, we can see the average time needed to infer the next observations. It can be observed that all classical methods are noticeably slower than the deep learning methods. The main reason for this is that the classical models need to be updated to the most recent observations to adapt to changes. This also explains the differences between the sampling rates. This contrasts with the deep learning methods where the models only need to be supplied with the most recent observations as input data for the context update. In summary, the deep learning methods require a notable amount of time for initial training, but are fast when doing prediction, whereas the classical methods are faster to fit while constantly requiring time-consuming updates. To conclude, both CNN and GRU have the best prediction performance across the majority of the datasets, while requiring more time for initial model training. However, depending on the use case, we found that there is always at least one classical model performing similarly well as the deep learning models, while being relatively fast to train. In general, the best performing models demonstrate to cope well, even though the amount of training data was limited. In terms of configuration, it is more straightforward to optimally configure the diverse classical methods. And based on our results, we deem both TES and the deep learning methods promising for use in the domain of DSPs. Here is our link to the GitHub repository. Thank you for listening, and goodbye.